right. Here in this video notes, we are going to be seeing how to solve two exercises for sections 13.9 and 13.10. So first, for this section, (13.9). And the example we're going to see is simple. I think in the exercises you can find on website, they are not very complicated. I think if you have learned how to use the methods that I explained in the previous sections, you will realize that they are not very complicated. So for example, the first one here is example. Find three integers x, y, and z such that their product is equal to 64. And the sum is a minimum. All right, first, you have to verify what is the function of several variables that you have to maximize or minimize, or in general, optimize. In this case, we have to minimize the function sum that I'm going to denote by only s. That is x plus y plus z. So in this case, we have a function of three variables, but we are not going to be working with this function because we have more information. We know that the product is of x, y, and z is 64. So we have to use this information to apply it here into this function. So what we can do is we can solve for z in this equation. Solve for z. In the equation x, y, z equal to 64. If we do that, we are going to obtain z equal to 64 divided by xy. There you have. Now substitute this into the sum. Into the sum function. So we have s is going to be x plus y. Wherever you see the c, replace the c by this expression. This one. So we have x plus y plus 64 divided by xy. Now, if you see, we have this has become a formula for function with only two variables. It's a function of several variables, but it has only two variables. Now, we have to minimize this function. We're going to be using the second partial test. But to do that, first, we need the partial derivatives. Partial derivative of s respect to x is equal to the derivative for this function, note, respect to x is going to be 1 here, respect to when we have y, is going to be only 0 because y is supposed to be constant when we are computing the derivative with respect to x. And here we have to compute the derivative for 64 divided by xy. Well, remember that the only variable is like the expression 1 over x. So 64 divided by y is constant, so we have to keep it there. The derivative for 1 over x is negative 1 over x squared, so the derivative is 1 minus 64 divided by x squared y. And in a similar way, we can find the derivative for respect to y, partial derivative. And this is 1 minus 64 divided by xy squared. Note that it's going to be almost the same because the derivative now, if we compute the derivative with respect to y, x is constant, so the derivative is 0. The derivative for y with respect to y is 1. And again here, 64 divided by x is constant with respect to y. So we have to compute only the derivative for 1 over y, that is negative 1 over y squared, times 64 over x. That's why we have this. Next, we have to find critical points. That is, we have to solve partial derivative respect to x equal to 0 and partial derivative respect to y, equal to 0. We have to solve this system of equations that becomes 1 minus 64 divided by x squared y equal to 0, 1 minus 64 divided by xy squared equal to 0. And we have to solve this system of equations. So from the first equation, we can try to re-express this from equation 1. We have add at both sides 64 divided by x squared y, so we can cancel this. And we're going to obtain 1 equal to 64 divided by x squared y. And if we multiply at both sides times x squared y, we're going to obtain this. This implies x squared y equal to 64. And there you have. This is from equation 1. And from equation 2, we can apply a similar reasoning. We have 1 equal to 64 divided by xy squared. And we're going to obtain xy squared is equal to 64, you see? So there you have this, we have this. Now, from this equation, x squared y equal to 64, solve for y, and what do we have? From this equation, we have y is equal to 64 divided by x squared, you see? And then substitute this into the equation 2. Substitute into this equation we just obtained. Xy squared equal to 64. And we're going to get x 64 divided by x squared raised to the square equal to 64. You see? And this becomes what? This becomes 64 raised to the square. Now we have 64 raised to the square, and we're going to have x squared raised to the 4, and raised to the square, that is going to be x squared raised to the 4, but times x is going to be x divided by 3, or x raised to the 3. Equal to 64. You see? From this raised to the square, 64 raised to the square, x squared raised to the square is x raised to the 4, but cancel one x with this x, we have x raised to the 3 in the bottom. And now we have only one equation for x. So for this, we are going to have x cubed. Note here, divide by 64 at both sides and multiply times x cubed at both sides. We're going to obtain x cubed equal to 64. And if you compute the cube root, we're going to have x equal to 4. And there you have the first solution for this. Now substitute in the equation 1. Now substitute x equal to 4 into this one, into this expression, y equal to 64 divided by x squared. And we're going to get y equal to 64 divided by 4 squared. And this is only 64 divided by 6. And this implies y equal to 4. So the critical points are, the only critical point is 4, 4. There you have. Now we have to prove that, we have to verify that this is actually a minimum, or the absolute minimum, or a relative minimum in a given region. But how to do that? Use the second partial test. Use the second partial test. And for this, we have to compute the determinant of the next matrix that I'm going to denote by D. And the matrix is, we have to find the second partial derivative with respect to x, evaluated at the given point, the derivative with respect to x and then y, evaluated at the given point, the derivative with respect to y and then with respect to x, evaluated at the given point, and the second derivative with respect to x, partial derivative, evaluated at the point AB. And we need to compute the determinant for this, and it's going to be partial derivative, second partial derivative with respect to x, AB, times second partial derivative with respect to x, respect to y, AB, minus derivative with respect to y, respect to x, then with respect to y, evaluated at a comma b raised to the squared. Yeah, remember this is going to be true because these two derivatives, these two partial derivatives, first respect to y and then respect to x, and the one first respect to x and then respect to y, they are mixed partial derivatives. They are equal under certain conditions. So for this function, for the function we're trying to minimize, that is true. So we can use, that's why I put here only fxy ab raised to the square. I could put down only fyx, right? Again, it's the same here because this and this, they are the same. Now for this we need the second, we need to compute this second partial derivatives. So the first one, second partial derivative with respect to x, is the derivative with respect to x of 1 minus 64 divided by x squared y. And what is that? This is going to be, well, the derivative of 1 is going to be 0, right? But here, the only thing, 64 divided by y is going to be constant. So we need to put down, let me write it like this. Partial derivative with respect to x, 1 minus 64 divided by y, x raised to the negative 2, you see? In this way, I think it's clear we can use the power rule for this. This is constant and this is 0 because the derivative of a constant when the constant is alone is 0. But this is multiplying the x, so we need to leave it there. So the derivative is 64 divided by y times negative 2 times, I'm sorry, I forgot this negative sign that is already there, right? So let me put it here, negative sign, times x raised to the negative 2 minus 1, negative 3. And if we simplify this, we're going to obtain 128 divided by yx cubed. And in the same way, we can do it for the second partial derivative with respect to y. Is the derivative with respect to y of the y derivative, right? That is the y derivative, this one. You see? This one. So 1 minus 64 divided by xy squared. And you can verify that it's going to be the almost the same as before, 128 divided by xy cubed. Now the mixed partial derivative fxy is the derivative with respect to y of 1 minus 64 divided by x squared y. And the same, I can re-express this as partial derivative with respect to y of 1 minus, in this case the y, the variable, so 64 divided by x squared times y raised to the negative 1 and the derivative is only negative 64 divided by x squared times negative 1 times y raised to negative 2. Simplify, and we're going to get 64 divided by x squared, y squared. You have. Now with this, we can compute d, right? Computation of d. Remember, we were doing this to compute d, right? Where do we have it? This d. All of this, all of this. So this means we have to evaluate the second partial derivative with respect to x at AB. The point AB is 4, 4. A, 4, B is 4. 4, 4. So wherever you see the x, replace the x by 4, and wherever you see the y, replace the y by 4 here. Here, here, and here. So what do we get? We're going to get d, sorry, d equal to 128 divided by 4, 4 raised to the 3, 128 divided by 4 times 4 raised to the 3 minus 64 divided by 4 raised to the 4. Yeah, again, I am using this formula, this one, that is given by f of x is this, f of y is this, and here, wherever you see the x, the y and the x, replace by 4, you see? Here is 4, 4, 4 squared and 4 squared is 4 raised to the 4. Do you have? And then let's continue here. And you will realize that if you do this, the d is going to be 0. So what is the conclusion here? Remember, the only conclusion you can get here is no conclusion. No conclusion can be obtained. We cannot use this method to evaluate this critical point. What do we have to do? Well, for example, we can use GeoGebra. So we have to use GeoGebra, right? So I'm going to use that because with this method, we cannot use the second partial test because when the d is equal to 0, the test says, oh, you cannot get a conclusion from here. It doesn't, remember, that doesn't mean that we don't have we don't have a minimum nor a maximum. No, it doesn't mean that. It means only we cannot provide a response to this question by using this method. So what we can do is we can use GeoGebra. I'm going to draw the function that we want to maximize. Remember this one. Where we have it here is this one, right? As x plus y 64 divided by xy. So let me do it. So we have f of xy equal to x plus y plus 64 divided by xy. And there you have, this is the function. Maybe you will have to make like a zoom here so you can detect the point 4, 4. Oh, I'm sorry, let me type the point, say A equal to the point 4, 4. Do you have a there? You see, it seems like it seems by now like it is only in the space and there's nothing. But I think it is because I haven't made a zoom in. So it doesn't seem to be there. Oh, I'm sorry, I wrote 65, right? I'm sorry, 64. X plus y plus 64 divided by xy. Let me draw this again because I think I have made a little mess. So I will try again. Type the function that you have and then the point. A equal to 4, comma 4. And there you have, that is the point. Again, it seems to be isolated, right? But the point is supposed to be reflecting the minimum. No, I'm sorry. Let me try again. The point 4, comma 4. Oh, I'm sorry. I had to put I'm forgetting to put 4 f of 4 comma 4. So it's 12. Yeah, I'm sorry. I was forgetting to put the other number. So the point is is 4 comma 4 comma 12. And there you have. You see? Now we can see it's a minimum, right? There you have a minimum. Yeah, I'm sorry. I was trying to put only the point 4 comma 4, but no, that is where the minimum occurs. But to identify or locate the whole point in this function, since it's a function of two variables, you have to put 4 comma 4 and the output given by the function at 4 comma 4. I mean, you have to evaluate the function at 4 comma 4. That is 12. That's why I had to put 4 comma 4 comma 12. You see? And there you have. This is the point. Yeah, I'm sorry. I was forgetting to put the other coordinate. Yeah. But you can see in this part, it's a minimum, right? It's a minimum. It's a minimum point related to this region. All right. So we can write the conclusion is we can write by using GeoGebra you can see that at 4, 4, there is a minimum. And the minimum is 12. So there you have. Now, but the question is, was to remember we're trying to find the three numbers, right? We started with this. We started to find three integers. I'm sorry. I think the problem was also that positive integers. So let me write it here. Positive integers. So x, y, and z. So we need to find c. Now, once we have found x and y, we have to find c, but c is only 64 divided by the product of x, y. You see this part. So to finish this, now c is 64 divided by xy. Substitute, we have 64 divided by 4 and 4, and this is only 4. So the c number is also 4. It's also 4. And there you have, you see? So the three numbers are 4, 4, 4. Find three positive integers such that the product is 64 and the sum is minimum. Those numbers are 4, 4, and 4. Their product is 64 and the sum of the three numbers is going to be the minimum, that is 12. Very well. Now, let's talk a little about Lagrange multipliers. 13.10 Lagrange multipliers. What is this? This is a method to find the maximum or minimum of a function f subject to a restriction given by a function of an equation in two variables, g of x, y equal to c. So when we have functions of two variables, like in this, like we have seen before, remember it's important to identify the region or the domain. The domain could be all the real numbers. Not all the real numbers. All the R2, that is all the Cartesian plane. But sometimes we can have only a region, right? For example, only for, like in the previous example, that we were focused only on positive integers, or we can have like a rectangle, or we can have any region that you can think of on the Cartesian plane. But here, when we are using Lagrange multipliers, we're trying to find the maximum, either the maximum or the minimum, but restricted to a very specific region given by an equation of two variables. In this case, given by an equation in the form g of x, y equal to c. It's going to be an equation of two variables. It's going to be a graph on the Cartesian plane. But our point is going to be what is the maximum or the minimum for the function f, yeah, but subject to this region, I mean in this region. So how to solve it? There is a method that we have to follow. Number one, solve the system of equations given by partial derivative with respect to x equal to lambda partial derivative of g with respect to x, partial derivative of f with respect to y equal to lambda partial derivative of y partial derivative of g with respect to y times lambda, and the equation g of xy equal to c. So it's going to be a system with three equations. We have to solve that. Number two, evaluate f at each point obtained from 1. The greatest value is the maximum, of the function f subject to g of x y equal to c, and the lowest is the minimum. So we have to, essentially, when we're using the Lagrange multipliers, we have to set up these equations. Note, they have to do with the partial derivatives for the function f, the one that we want to optimize, and this restriction that is a function of two variables, well, an equation of two variables, g of xy equal to c. We have to solve this equation for xy on lambda, and once we have done that, we have to evaluate those values for x and y that we obtain at the function f. At the function f, and then the greatest is going to be the maximum, and the lowest is going to be the minimum. All right, let's see one example for this. So a typical problem for Lagrange multipliers starts like this. Example, maximize the function f of xy equal to x times y subject to x plus y equal to 4. So this is a simple example, but it's perfect to illustrate the ideas behind this method. So we're given one function of two variables, and then we have a restriction. By the way, the whole domain, the maximum possible domain for this function is all R2. That means all the whole Cartesian plane, but we don't want to find the maximum there because in that region, I mean in the whole R2 or Cartesian plane, this function doesn't have a maximum. But if we restrict to this region, to the line x plus y equal to 4, then we're going to be able to find a maximum and a minimum by using the Lagrange multipliers method. First, we have to find partial derivative with respect to x. Partial derivative with respect to x is only y. Partial derivative with respect to y is only x. Partial derivative of y with respect to x is only 1. And partial derivative with respect to y of y is only 1. I'm sorry, I forgot to mention that it's important to identify the function g. Note, you are going to be given a restriction, but you have to write it in the form g of xy equal to c. In this case, I have x plus y equal to 4. So this can be expressed as g of xy equal to 4. So in this case, in this particular case, g of xy is only x plus y. See? There you have. So don't forget that. X plus y, then g of xy is x plus y. If, for example, you have a restriction in two variables where one of the unknowns is in the other, or the variables is in the other side, and you have one unknown in the other side too, no problem. Arrange this so that you can have all the unknowns in the left-hand side, and then identify that expression as g of xy. You see? There you have that. And then the derivative for x, here's respect to x is 1, and respect to y is 1. Now set up equations. Solve partial derivative respect to x equal to lambda partial derivative respect to x of g, partial derivative of x respect to y equal to lambda partial derivative with respect to y, and g of xy equal to c. And this becomes what? This becomes y equal to lambda, x equal to lambda, and x plus y equal to 14. So it's going to be a system of three equations with three unknowns, but our concern is only x and y. Solve for x and y. No, since x is equal to y equal to lambda, from here, right? Y equal to lambda, x equal to lambda. So it's x equal to y equal to lambda. We can have that. Substitute this into the third equation. We have x plus x equal to 14, and this implies 2x equal to 14 divided by 2, and we have x equal to 7. They have one value for x, you see. I substituted x equal to y into the third equation, y by x. That's why I got x plus x equal to 14. So for x is x equal to 7. And now we need to solve for y. But since x equal to y, we have also what? That y is equal to 7. Now evaluate the point 7, 7 at the function f. And this is f of 7, 7 is equal to 49. And there you have. This proves that if this function has a minimum at this function restricted to the line x plus y equal to 4, to this line, then it has to occur at 7,7 and its value is 49. All right, so you see, applying the Lagrange multipliers method, I think it's not very complicated. Maybe it would be if we have a complicated functions, but the essential idea, I think, is not very complicated. All right, that's all by now. See you.